In today's class, we're going to be talking about rate of change, more specifically how to figure out instantaneous rate of change and average rate of change. Now, before I begin the lesson, I do use acronyms for instantaneous rate of change and average rate of change. So for instantaneous rate of change, I use IROC, and then for average rate of change, I use AROC. So sometimes you'll see me write that in my notes. That's just what it stands for. Now, you might be thinking, how is what we learned yesterday, which was the slope of a tangent, relative to what we're learning today? Well, let me start off by explaining the first thing. If I asked you to figure out the slope of a secant line for a curve, most of you would have no problems. The reasoning behind that is because a secant line touches your curve at two different points, so it's easy to figure out the slope there. And the slope of a secant line actually represents the average rate of change. Let me erase that. It represents, like I said, our average rate of change. Now, yesterday we talked about the slope of a tangent, and we ran into an issue because a tangent line only touches a curve at one point. And so we had our special formula from yesterday to help us figure out the slope of a tangent. Now, the slope of the tangent, if we make some connections, actually represents the instantaneous rate of change instead. So anytime you hear in a question that it's asking you to find the slope of the tangent, remember that you're technically finding the instantaneous rate of change. If you see a question that asks you about the instantaneous rate of change, it means you're asking about the slope of the tangent line then. So I'm going to keep that up at the top for you so that you can kind of keep that in the back of your head. Because a lot of the times I find students, they kind of freeze up when I say, find me the instantaneous rate of change. And then they go, well, I don't know how to find it, miss. And I'm like, technically you do. You just find the slope of the tangent line. So let's take a look at part one. So part one here talks about average rate of change versus instantaneous rate of change. And we're going to take a look at our first example to help us out. So in this first example, it says, use the distance time graph below to answer the following questions. Question A asks, what's the independent variable and what's the dependent variable? So based on our graph here, and most of you are going to be pretty comfortable indicating what your independent and dependent variables are, based on the fact that you know that your independent variable is always on your x-axis, and then your dependent variable is always on your y-axis. So based on this idea, I know that my independent variable is going to be time, which is in seconds, and then my dependent variable is going to be distance in meters. Let's take a look at example B, or part B. So for part B, it says, in what units is the rate of change going to be expressed as? So if you were to find average rate of change or instantaneous rate of change, there's a unit that's going to be attached. Anytime you're finding the rate of change, the units are always going to be expressed as the following. It's always going to be your dependent variable divided by your independent variable, or the units for your dependent and your independent variable. So in this particular case, my dependent variable is distance in meters, and then my independent variable is time in seconds. So my rate of change is going to be meters per second. So regardless of the question, it's always important for you to identify your independent variable and your dependent variable and know what units each of those variables have so that you can actually have the units for your rate of change. Let's take a look at C now. So for question C, it says, explain how you would find the average velocity of an object between 1 and 13 seconds. Now, the word gives it away a little bit, average velocity. This is essentially asking you to find the average rate of change. Now, if you're questioning, miss, let's say you didn't put in the word average there. How would I know that I'm looking for average rate of change? The other dead giveaway is that I'm giving you a time interval between 1 and 13 seconds. If ever I ask you to find the rate of change and I give you a time interval, so between one time and another, then you're finding average rate of change for me. So if I look back up to the graph, I'm going to show you how to find your average rate of change. So for my average rate of change, I'm focused on from 1 second to 13 seconds. So at 1 second, I'm looking at this point on my graph. And then at 13 seconds, I'm looking at this point on my graph. I'm going to connect those 2 points together now using a secant line, just like this. Oops. And so this line here, the purple line that I've created, that's the secant line that's going to help us figure out our average rate of change. So secant line for average rate of change. So let's go back down to the question again. So for C, it asks you to explain. So what we did first was we drew the secant line. Drew secant line with points at t equals to 1 and t equals to 13. Once we drew the secant line, we can use the ordered pairs from when time is 1 and when time is 13 to figure out the slope of that line. So the second step would be to find the slope of the secant line. And that will tell you your average rate of change. So when your distance related to 13 seconds minus your distance related to 1 second over 13 minus 1. So this is your regular slope formula. Because I don't actually have a function that indicates the distance at those particular times, that's why you see me say the distance at 13 seconds and then the distance at 1 second. So that's dealing with average rate of change, or average velocity in this particular case, because we're dealing with meters per second. Now, part D says, explain how you will find the instantaneous velocity of an object at 14 seconds. Now, again, the words give it away. This one here, you're actually figuring out your IROC, or your instantaneous rate of change. But then again, you think to yourself, miss, what if you didn't tell us it was instantaneous? How would we know? Well, we're going to take a look at the back. Notice here how I'm looking at the velocity at a particular time only. So I'm not looking at an interval of time periods. I'm only looking at one specific time. At this particular case, at 14 seconds. So that's how we know that we're figuring out an instantaneous rate of change. If I'm looking at a particular time or a particular point only. So let's figure out how we would figure out our instantaneous rate of change. Now in this particular case, because we don't have a physical function to work with, we are going to have to hand draw our tangent line. And I know in the previous class I had said, hand drawing tangent lines are a no-no. But in this particular case, I don't have a function where I can use that formula that I learned about yesterday. So let's take a look up at the graph. So on the graph here, I'm going to indicate the point on the graph related to t equals to 14 seconds. So in this particular case, it would be this point here. So what I'm going to do is I'm going to try to draw my best tangent line at that point. So I'm going to try to draw the best one that I can. Like I said, whenever you're hand drawing your tangent lines, it's not that great. So this here, this is your tangent line for your instantaneous rate of change. Now, because I said here, there's no formula, we have to rely on what we have graphically. So I'm going to scroll back down. And for question D, the first part that we did here was that we drew a tangent line at t equals to 14 seconds. And then in order to figure out the instantaneous rate of change, like I said, since we don't have a formula, we would have to figure out the slope graphically by looking at rise over run. So since there is no equation for this graph, will have to look at the slope of the tangent graphically. In other words, to figure out your instantaneous rate of change here, you're going to rely on the old-fashioned slope, which is your rise over your run. So that's how you differentiate between average rate of change versus instantaneous rate of change. Let's take a look at examples that include equations and see how that differs for us now. Alrighty, so let's take a look at finding rate of change using equations. And this is oftentimes the one that most of us will rely on. So in this example here, for example 2a, it says a toy rocket is launched straight up so that its height, s in meters, at time t in seconds, is given by s of t equals to negative 5t squared plus 30t plus 2. And it asks, what's the average velocity of the rocket between 2 and 4 seconds? The question gave it away that we were looking for average velocity, but the dead giveaway is the interval, the time interval that I gave you between 2 and 4 seconds. So to figure out our average velocity, you know the time interval there. So what we're going to do is we're going to figure out the ordered pair associated with 2 seconds and then the ordered pair associated with 4 seconds. So let's start off with 2 seconds. So I'm going to do s of 2. I'm going to get negative 5 times 2 squared plus 30 times 2 plus 2. If I simplify that, I'm going to end up getting 42, which means my first ordered pair here is 2 and 42. I'm also going to do the same thing for 4 seconds. I'm going to find s at 4. So I'm going to do negative 5 times 4 squared plus 30 times 4 plus 2. If I simplify, I'm going to get 42 as well. So my second ordered pair is going to be 4 and 42. Remember, to find average rate of change, you need 2 ordered pairs, which is what we have here. And so now what we're going to do is we're going to go and do the old-fashioned slope formula. y2 minus y1 divided by x2 minus x1. So I'm just going to label everything so that it's a little bit more apparent. And to find my average velocity now, or my AROC, I'm going to do 42, which is my y2 minus 42, over x2, which is 4 minus 2. That's going to give me 0 over 2, which simplifies to 0. Now this means that my average rate of change is 0 here, or 0 meters per second. You have to include units. So therefore, the average velocity is 0 meters per second. Let's take a look at 2b. I'm just going to scroll the page just a little bit down so that I have enough space to do the question. So for 2b, it says, what is the velocity of the rocket after 5 seconds? Now, when you take a look at this question, you're like, okay, I don't see any words like average or instantaneous. So I don't know which one I'm looking at or looking for. But then you notice, Miss Lim only gave me one particular time, which means I'm looking at a particular time or a particular point. So this means that I'm looking at the instantaneous rate of change here instead. So for instantaneous rate of change, remember what we did yesterday. The first thing that you have to figure out is essentially the slope of your tangent. That's instantaneous rate of change. So let me write that so we always remember. This question talked about instantaneous rate of change, which is really talking about the slope of our tangent. So we're going to follow the steps that we did for finding the slope of our tangent. The first thing that we're going to do is we're going to figure out s of 5. So I'm going to do negative 5 times 5 squared plus 30 times 5 plus 2. And that's going to simplify to 27 for us. Remember our second step. Because we're finding the slope of the tangent, we need to take a look at another point. We're trying to mimic a second point to help us figure out our slope of our tangent. So in order to do that, it was going to be 5 plus h. And so that means I'm plugging in 5 plus h everywhere I see x, or everywhere I see t in my equation here. So exactly like what I'm doing. And then I'm going to simplify this. Now, when I simplify this, I'm not going to show all the work, but you're going to end up getting negative 5h squared minus 20h, and then plus 27. So now that I've gotten s of 5 and I've gotten s of 5 plus h, I'm going to use the formula from yesterday to help me figure out my instantaneous rate of change now. So to figure out my instantaneous rate of change, I'm doing the limit as h approaches 0, and I'm doing it for s of 5 plus h minus s of 5 all over h. So let's plug everything in and let's see what we get here. So I'm going to have negative 5h squared minus 20h plus 27 minus 27 all over h. So right away I notice, I can simplify some things. So I'm just going to scroll down. So if I simplify, I'm going to get the limit as h approaches 0. The positive 27 and the negative 27 cancel each other out. I'm going to factor out the h, so I'm going to get negative 5h minus 20 all over h. The h's will cancel out here, so I'm going to cancel out my h's, and then I'm going to be left with the limit as h approaches 0, and I've got negative 5h minus 20, and now I notice that if I plug in 0, it's not going to cause me any problems, so I'm going to evaluate my limit now. So if I do that, I'm going to do negative 5 times 0 minus 20, and that's going to give me negative 20. Now, remember your units here. This is meters per second. And so what this indicates here is that the velocity, or the instantaneous velocity of my rocket after 5 seconds, is negative 20 meters per second. So I'm just going to write here, therefore, the instantaneous, Miss Lim has to remember how to spell instantaneous, the instantaneous velocity is negative 20 meters per second. Now, if you think about it in terms of direction, up would be positive. So negative here would mean that technically our rocket is falling at 5 seconds. It's actually falling down. So that's kind of how you can put together rate of change in terms of direction, since we see negative here.